Alrighty, hello and good afternoon. Welcome to lecture, Wednesday lecture. We are 1 week into October, and I don't know about you, but I am enjoying the not quite as hot weather. It's fall if you squint your eyes and use your imagination. Grateful that it's not triple digits. I'll take low 90s anytime. Let's see. Okay, I don't really have any new announcements. There's I made a post about exam 2 with as much information as I can. The one piece of information that isn't present at this moment in time is the time that you'll have on the exam. You can expect about 2 minutes a problem. That's around what the first one was, but the reason why I don't know is I haven't finished writing it. Once I finish writing it, I'm going to take the exam myself and use that, how long it takes me, to determine how long you'll get. So since it's not finished, I don't know the specific time. You can expect roughly the same amount of crunch, but I will post what I know. But honestly, I may not know till like tomorrow. And it launches Friday night. Yes, Amanda. I think so. Okay, so Amanda asked if we will be having regularly scheduled lecture on Monday. Yes, unless Monday's a holiday. Let's see, that would be the 10/12. Let me Google that really quick. I don't... Here, let me pull up the lecture syllabus. I don't think it's a holiday. If it is, that FLC observes. Let me see. Let's pull up the lecture syllabus. Let's go to the schedule. It's that 10/12. Yep, totally. I guess it's Columbus Day. Columbus Day is something that K through 12 get off, but college doesn't take that off. So yeah, we totally have normal lecture and yeah, lecture and office hours. You are welcome, Amanda. Let's see. Emma, your question is good. Emma had a question about the exam review packet. The question was, do we need to print it out, or can we just write out the problems? Totally do the problems on the worksheet as I gave it. So either print it out and then use like Adobe Scan on your phone to take high quality images and then submit that as a PDF. Or I'm also totally fine if you want to do your work digitally, like write in it digitally. If you have a tablet, or even if you don't, if you have a computer, there's PDF editors. But either way, directly into the worksheet. You are totally welcome. Will I totally feed ya, feel ya. I feel like yeah, totally. Yeah, I yeah. Yep. You know, it's a chemistry class. I try not to get political or whatever, but I do feel fine saying that don't think Christopher Columbus is a person worth celebrating. So I'm all in for Indigenous Peoples Day. But Indigenous Peoples Day is also not recognized by Folsom Lake College, and we're following the official college schedule. So, yep, normal classes on Monday. It'll be good. Okay, let's see. So we have one last thing to talk about with acid-base chemistry, and this actually is more of a tie-in with chapter 5. So if you were if you attended my lab lecture on Monday, or if you watched it later and we talked about gas laws, this is really a tie-in with that stuff. The last thing we have to talk about in chapter 4 are what are called gas evolving. Gas evolving reactions. Gas evolving reactions. And there are certain acid-base reactions that, by gas evolving, all that means is gas producing. There's some acid-base reactions that produce gases as a product, and this will tie in with the chapter 5 material, because chapter 5 is about the gas phase. And so I'm going to go over these briefly. It's nothing really new. These aren't things you have to memorize, but these are things you're going to see with more regularity as we I was about to say, as we get into chapter 5. We've actually already covered chapter 5. So as you do chapter 5 material, you'll see problems like this, like these, or reactions like these will show up in problems. That's what I was trying to say. So the first set of gas evolving reactions I want to talk about are reactions of carbonate or bicarbonate so carbonates or bicarbonate ionic salts, if that's the anion, these react with acids to produce a gas, all right? And in general, the equation that you'll see is you have aqueous acids reacting with either a carbonate or bicarbonate ionic compound. These are paired with some metal. And I'm going to put a question mark here for the phase, because the phase depends upon what metal we're dealing with. If it's one of our always soluble ones, sodium, potassium, lithium, ammonium, they'll be aqueous. If they're not, carbonate's insoluble, so they'll be solid. So the phase here can change. But when you react them with an aqueous acid, doesn't matter what the acid is, you're going to get you're going to produce carbon dioxide gas, liquid water, and a salt. All right? And just like with our neutralization reactions, the salt is going to be based on the metal cation that's paired with the carbonate and the anion that the acid is based on, right? So this salt will be made up of your metal cation plus whatever anion is left over after the acid is stripped of its protons. All right. Something that I want to point out is the reaction is the same regardless of whether you have a metal carbonate or a metal bicarbonate. So either or, the products are always the same. It's CO2, water, and your salt. All right. Another gas evolving reaction that's pretty much the same is the reactions of sulfites or bisulfites with acids. Right, when you react these ionic salts with acids, what you end up getting is the following reaction. Again, aqueous acid reacting with your sulfite, which, sorry, not sulfate, sulfite, which will be paired with some metal cation. And the products here will be SO2 gas, so sulfur dioxide. Oh, also the solubility here depends upon the solubility rules. Sulfur dioxide plus H2O liquid plus our salt again. And the salt is composed of the metal cation pairing with the anion that's left after the acid reacts completely. And just like the previous example, this reaction's products are the same whether you're using a sulfite or a bisulfite salt. All right, the products will always be SO2, H2O, and a salt. All right, here, hang on 1 second. Okay, actually, it sounds like that. Oh wait, hang on. Sorry about that. My wife was having a conversation literally on the other side of the wall. She didn't realize that the stream had started. Okay, so those are gas evolving reactions with carbonates and with sulfites. There's a third gas evolving reaction. If you react a sulfide with an acid, you're going to get, so here we'll have our aqueous acid plus our metal sulfide, whatever solubility that salt has. These reactions produce dihydrogen monosulfide gas plus the salt that we're getting very familiar with seeing. So this is the identity of our salts. All right, and so those are three acid-based gas evolving reactions, and the last one is going to be with base, and that is anytime you have an ammonium salt, all right, reacting with a base. All right, in these reactions, you'll have your ammonium salt, which will come with a counterion, an anion, plus some base, which is going to be a hydroxide base, right? A metal hydroxide. And the gas that evolves from this reaction is ammonia. You also make liquid water. Sorry, I should put a question mark for the phase of our metal hydroxide. Plus our salt. And the salt here is based on the metal from the metal hydroxide plus the anion from your ammonium salt. So a little different than your acid-base situations, but not that earth-shattering. All right, and again, those reactions are, you don't have to memorize them, but I want you to be aware that they exist. They'll come into play with the gas law stuff. Sorry, chapter 5. So really, I'm not planning on including these on exam 2, but they're definitely a strong candidate for exam 3 problems. All right, and that is the end of chapter 4. We've now covered everything that will be on the second exam. And we're going to dive into chapter 6. And again, if you're wondering, wait, chapter 6, what happened to chapter 5? Those were covered. Those were covered in lab. We did 2 lab lectures on chapter 5. So you can go and watch those at your leisure. Kate, great question. Kate asked, would the ammonium salts be in the aqueous phase? And the answer is yes, because ammonium is always soluble. Right, ammonium is on our always soluble list. So whatever anion it's paired with, it will be water soluble. It'll be in the aqueous phase. All right. So chapter 6, shifting gears here. Chapter 6, we're going to be looking at one thing. We're going to be studying one thing, and that thing is energy. All right. Energy. Now, if we're going to be studying energy, probably a good place to begin is, well, what is energy? Let's see. Jared, great question. Jared asked, is it going to be hard for us to understand chapter 6 if we haven't started chapter 5? And the answer is not at all, but I guess I should qualify that not at all at first. There is some stuff with chapter 6 where you do need to kind of have a background in the gas laws. But that isn't till we're not going to get to that for a lecture or 2. So I would recommend maybe starting to do the gas law stuff. Just watch it, kind of absorb it. But the thing to watch out for is once we hit work in this chapter, which is a technical scientific term, we'll be talking about it. Once we hit work, that's where a little bit of gas law stuff will come into play. With pressure and whatnot, so you don't have to worry about that for a little bit. But at the beginning, it's just a completely different thing. All right. Okay, so we're talking about energy, right? We're talking about energy, and a good question to ask would be, well, what is energy? All right. What is energy? Where's Photoshop? Here's what is energy? Where is Photoshop? what is energy? All right, and if you crack open your physics textbook, right, or even ask your resident physicist or chemist for that matter, this question, what is energy? You'll most likely get the answer that energy is the ability to do work. Right? That we, oh, hang on. If you look up a definition for energy in any science textbook, no matter where that textbook came from, even your high school texts, you'll get energy is the ability to do work. And this will be quickly followed by a second definition where they'll hurriedly, and I would hurriedly, follow up with, and work, by the way, is a force applied over a distance. All right, energy is the ability to do work, and work is a force applied over a distance. Now, I want to pause real quick because I pulled a fast one, and physics has pulled a fast one. You'll notice that the original problem is what is energy, and the answer that I gave was the ability to do work. Notice this is subtle. I didn't ask what can energy do, because this definition tells you what energy does. Energy does work. I didn't ask what it could do. I asked, what is it? What is energy? Right? Do you want to know what energy actually is? Like, what is its essence? Here's the thing. If you want to know, I do too. I have no idea what it is. We know it doesn't have mass. We know that energy doesn't have mass. We know it's got some particle wave duality, like it's mostly a wave, but it's a little bit like a particle. But if you ask me straight up to tell you what is energy, I can tell you what it does. I can tell you some attributes, but I don't actually know what it is. So, if you want to know what energy is, go get your PhD in physics, come back, and please tell me, because I'm dying to know. All right? There's still really cool stuff out there that needs to be interrogated, and if you're curious enough, you might be the person to do it. All right, but enough of a plug for grad school and whatnot. Let's come back to Chem 400. So we don't know what it is. We do know what it can do. Energy is the ability to do work. We'll talk more about work at a later point. That's where the gas laws will come in. But for now, we're just going to have to be content knowing what it has the ability to do. And I'm going to add a little bit to our vocabulary and our understanding of what we do know about it. All right, and one of the things that we know about energy is energy comes in two different flavors. There's two distinct types of energy that we see in the physical universe. Not good energy and bad energy. There's kinetic energy and potential energy. And by the way, from this point on, I'm going to write energy as just a capital E, because I don't have the patience to write the nergy that comes after it. All right, kinetic energy is, oops, I want that in black. There we go. Kinetic energy is energy associated with motion all right? The energy that is associated with motion and potential energy is the energy that is associated with position or composition. Right? It is the energy associated with where something is located or what it's made out of, its structure. All right? Now, these are both very broad kind of definitions, categorizations, and we could break it down into different types of kinetic energy, different types of potential energy, because there are different ways of kind of categorizing, quantifying. But this is not a physics class, this is a chemistry class. And so we're approaching both of these things from a very chemical perspective. So in this class, when we talk about kinetic energy, our focus is not going to be, you're not going to be doing those problems. For those of you who've taken physics, you've done plenty of these, where it's like a word problem, where it's like, I throw the ball, and based on its velocity, how much kinetic energy does it have? We could do that, but not in this class, because we don't throw balls in chemistry, right? We're interested in molecules. And the type of energy that we're going to focus on for kinetic energy is known as thermal energy. Thermal energy. Another way to think of this is as heat or energy associated with temperature. Right? So like the hotter something is, the more thermal energy, the more kinetic energy it has. The colder something is, the less kinetic energy or thermal energy it has. And again, from a chemical perspective, when we talk about potential energy in the context of this class, sometimes this is called chemical energy, which is stored. It's the energy stored inside bonds. All right. So the actual bonds in a molecule store potential energy. That's why when you light something on fire, by the way, and it's hot, you're burning it, you are igniting a reaction. You're starting a reaction that is breaking bonds, and the breaking of those bonds is releasing energy into its environment. So that's why explosions can be so crazy. You've got some bonds that are very, very high energy, but it's potential. And when you blow up, when you detonate, it releases that energy in a huge wave of kinetic energy, transforms it from potential to kinetic. All right, so those are kind of this is the lens here. Thermal energy for kinetic and chemical energy for potential, that we're going to be looking at these two types of energy, because after all, this is a chemistry course. All right. Now, before we move any further, we've got some other stuff to talk about, but I do want to say that I want to talk for a moment about units. All right, energy units that you'll run into. So the standard unit for the metric system is the joule. The standard energy unit for the English system is the calorie. All right, and I just want to again, these might be these unit conversions may be good things to put on your equation sheets for an exam, so you have them at the ready, right, to to use if you have to do a unit conversion on an exam. Not exam 2, by the way. This is all exam 3 material. But the unit conversion from joules to calories is as follows. 1 calorie is the same as 184 joules, and that is not exact, right, because you're going English to metric. Now, we're all familiar with the word calorie because it's plastered all over our nutrition facts boxes, right? But one thing you'll notice is on the back of our food boxes, calorie is capitalized. And turns out that a capital C calorie is different than a lower C calorie. 1 capital C calorie is worth 1,000 lowercase c calories. And you might be going, that's lame. Why don't they just call them kilocalories? The answer is it's the English system. We don't have prefixes. We don't use them. So we do dumb stuff like this. All right. So 1 calorie is worth 1,000 calories. 1 capital C calorie is worth 1,000 lower C calories. Another unit that you really don't see all that often, unless you are from an engineering background, is something called the kilowatt hour. 1 kilowatt hour is 3.60 times 10 to the 6th joules. This is something that you may come up, you may find in the problems where they give you energy in kilowatt hours. And so I just want you to have these unit conversions. They tend to be the most helpful as you move through the homeworks. All right. So now that we've talked about units, we've gotten that out of the way. Let's start talking a little bit about about some thermodynamics. All right. So the first, well, actually, before we even talk about the first law of thermodynamics, we need to talk about a different law, which is the law of energy conservation. All right, the law of energy conservation, simply states that energy is not created or destroyed. All right. Energy is not created or destroyed. It can only change form. All right. That is the law of energy conservation. Kate, great question. Yes, if you were wondering, the unit conversion from kilowatt hours to joules is inexact. Kilowatt hour is another, an alternate energy unit in the English system, I think. I don't know for sure. But yeah, that is it. I do know for sure that it's an inexact conversion. So it will limit your sig figs. All right, so that is the law of energy conservation. Energy is not created or destroyed. It can only change form. All right, and we'll see in this chapter, we'll start looking at reactions, whether or not they absorb or release energy, and we'll see that it's just this constant energy exchange. Really, all chemistry and physics is trading energy back and forth between as reactants transform to products from systems to surroundings. It's this ongoing, never-ending saga. All right, that's the law of energy conservation. When you take the law of energy conservation in stride with something called the first law of thermodynamics, we learned something interesting about the universe. All right, so here is the first law of thermodynamics. So the first law of thermodynamics states that the total energy of the universe is constant. All right, the total energy of the universe is constant. The universe, if you add up all the energy present, that amount does not change. All right, it is not gaining energy, it's not losing energy, it's the same. All right, and when you pair these two together, that energy isn't created or destroyed, it only changes form, and the total energy of the universe is constant, doesn't change. You get something very, very critical for our understanding of energy and of thermodynamics and thermochemistry by proxy, and that is no free lunch. You cannot get something for nothing. There is no free energy. Like we can just make it out of nothing. It's got to come from somewhere. If we're going to gain it, we have to deplete something else, somewhere else, right? You can't get something for nothing. It tells us that energy cannot be generated in the truest sense of that word. It can't be generated. It can only be converted. From something else. All right. Now, when you hear the word energy, because we talk about power plants generate energy, right? That word is used kind of loosely, and in the strictest physical sense, it's not being generated, because generated makes it sound like, oh, you're producing it, you're making it, when in reality, every single power plant out there, no matter what the type, whether it's coal, hydroelectric, wind-powered, nuclear, it is taking energy from a source and changing its form, converting it to the electricity that we use to power all of our stuff. Whether it's thermally by burning coal, whether it's thermally by running a nuclear reaction, whether it's taking the kinetic energy of wind or water flowing and taking that energy and converting it into electricity, we're always siphoning energy out of something else into the form that we use. So it's important, I think, to understand that distinction. So when you hear people talking about energy sources, know that those sources actually are a resource, and a resource that gets depleted by using them, right? I think that the best energy source that we have is the sun, because yes, we're still consuming it, right? But it's burning no matter what. We have no control of that. That energy is hitting Earth, and it's ours to do what we wish, and there's a lot of it. But even then, we're taking energy, converting it, changing its form. So when you hear about new ways, yes, Tyrese, straight up. It is equivalent exchange. So don't let anybody tell you that you didn't learn anything from watching Full Metal Alchemist. All right, and if you haven't, give it a try. You might actually learn something. Okay, so I have belabored that point long enough. Let's start talking about. So we've been talking conceptually about energy, about it changing form, converting it from one form to another. Let's actually start talking brass tacks about how energy changes form. Okay, so energy. So there are two energy flows. All right, there's two ways that energy can move. All right. And this is going to get a little conceptual. So energy can flow almost philosophical in two directions. All right. Energy can flow from the system, can flow out of the system into the surroundings, all right, that is one way. Energy can flow from the system to the surroundings. Energy can also flow from the surroundings into the system. All right, those are the two directions energy can flow. Now you may be wondering, what is the system? What is the surroundings? And the system is always whatever you're studying. Whatever you happen to be studying, whatever you are studying. All right, so the system may be as small as an individual reaction. The system could even be more specific. If you have a reaction happening inside a solution, your system might be your solute, just your solute, not your solvent, right? The system could be as large as planet Earth, or our solar system, or our galaxy, what have you. It's whatever scale you're studying on. The system is that thing you're focusing on, and the surroundings are defined by the system. All right, the surroundings are defined as everything else. So the system is what you're studying. The surroundings are the rest of the universe, all right? That is the two things. So either you're looking at a specific thing, right? You're looking at a specific thing, and either energy is flowing from your thing out into the rest of the universe, or energy is going from the rest of the universe into that thing you're studying, all right? Those are the two directions energy can flow, all right? And so there's two directions energy can flow, and there are two mechanisms by which energy can flow, all right? So we have our system, and we have our surroundings, and we know energy can go back and forth from the system to the surroundings, right, and vice versa. But there are actually two distinct ways in which energy travels from system to surroundings and from surroundings to system. One path is thermally. So you can have what's known as thermal energy transfer, which is symbolized by a lowercase q. And then the other way that energy can be transferred back and forth is through work, which work is symbolized with a lowercase w. And when we talk about energy transfer through work, that's the moment where it might be helpful to have seen the gas laws lecture. So eventually we'll get there, we'll get to work, but we're going to start with thermal energy transfer. All right. So let's talk just for a minute. Well, I'm going to say something about both of them, and then we'll get more brass tacks. So when we talk about thermal energy, which is a Q, this one makes more intuitive sense, right? This is simply it's heat transfer. When you grab your cup of hot coffee, right? When you grab your cup of hot coffee, as I'm doing now, you feel the warmth on your fingers. If you're looking at that coffee as being the system, when you touch, or let me grab the actual cup. When you touch it, right, you feel warmth from the cup going into your fingers. The reason why you feel warm is because you are absorbing energy out of the coffee into your hand. If the coffee's the system, my body's part of the surroundings, and so that would be system to surrounding thermal transfer. All right? When you touch something cold, like, I didn't even plan to have hot and cold props, but I just do today. All right? Like this. Oh, wait. Like this. Off-brand Kirkland LaCroix. That's not as good as the real thing, but it's cheaper, so I buy it. This is cold. When my hand feels cold, if this is my surroundings, the reason why I'm feeling cold is because if this is the system, the system is drawing energy out of my body. Thermal energy is being transferred from my body, the surroundings, into the can, the system. And so that's thermal energy transfer as well. Heat transfer makes intuitive sense because we touch hot things, we touch cold things, and we know what they feel. And so it helps us make that connection. All right. Work is a little more abstract, which is part of the reason why we're going to talk about it in a second. The other part is to give everyone a chance to watch the Chapter 5 lectures. Work is a little more abstract, right? Work is defined as a force applied over a distance, and energy is defined as the ability to do work. So work is an energy transfer mechanism. There are many ways that energy can be transferred through work. If you've had physics, you already know that's the case. All right. In this class, the most processes don't involve energy transferred through work. There is one that does, though. In a chemical context, work happens because energy is transferred by, or I should say through, the expansion or compression of a gas. So if you have a sample of gas that expands or is compressed, energy will be transferred through work, and it may be independent of thermal energy transfer. It's a little more abstract. We're going to get to it eventually, but we're not going to talk about it now. Suffice it to say, the last thing I'll say before we zero in on thermal energy, and I need to give myself a little more space at the bottom of this page. The final thing that I will say is that, oops, hang on. There we go. If we want to talk about total our total energy transfer. Total energy transfer can be calculated with an equation that looks like this. That total energy transferred will equal is a delta E, all right? And your change in energy is equal to the amount of thermal energy transferred plus the amount of work energy transferred, all right? This is an equation that we will be coming back to once we know what Q and E are, once we've interrogated both of those processes individually, then we'll bring it back home and talk about the thing all together. I said that was the one last thing before we dived into thermal energy, but there's one thing before that. Regardless of the energy transfer mechanism, whether it's total energy, whether it's just thermal, or whether it's just work, the sign of these transfers are important. If your energy transfer is a negative number, all right, this means that energy is released, all right? In other words, it goes from your system to your surroundings. And it is called exothermic. It's called exothermic because it's hot to the touch when energy is being released into the surroundings. Because when you touch something, the system is that thing that's burning, that's on fire, and you're feeling that heat coming off of it. If your energy transfer is a positive number, that means energy is absorbed. All right. In other words, energy is flowing from the surroundings into the system. All right. And we would say that this is an endothermic process. All right. And with that under our belts, that vocabulary and those concepts, we can now begin a discussion of thermal energy transfer. All right. And so I'm going to create a new banner. We're going to talk about Q, which is thermal energy transfer. So, now even in our casual discussion here, we've been talking, when we've talked about thermal energy, we've talked about heat, right? And it's impossible to say the word heat without thinking of temperature, which is natural, right? Something that has a high temperature, we say is hot. Something that has a low temperature, we say it's cold. And so temperature and heat are, in our English vernacular, are kind of used interchangeably. But if you look at them in a scientific setting, they're actually different quantities. They're distinct quantities, which is why they're measured in different units. All right. Q is measured in joules. Temperature is measured in degrees Celsius or Kelvin, right, or Fahrenheit, but it's a different unit. Temperature units are different than the units used to measure energy. All right. Just a quick aside, just to make sure we're all on the same page. This right here is the Greek letter delta. And it means, whenever you see a delta, capital delta, that's what that triangle is. It always means change in. All right, so change in volume, change in pressure, change in temperature. That's what that delta means. And anytime you see it, it means the final state minus the initial state. That's the definition of delta. You'd have delta T, delta E, delta V, delta anything. All right? So this is change in temperature. And the reason why that is delta T is because Q is the change in thermal energy. All right, so that's why we are dealing with a change in temperature. We're not looking at a static measure of the thermal energy of the system. We're looking at how it's changing. Is it gaining or losing energy? All right. So Q and delta T are different quantities. Temperature, change in temperature, and change in energy are different quantities, but they're proportional to each other. All right, and this is the This is the Greek symbol alpha. It means proportional to, and it's simply because when temperature increases, the amount of thermal energy in the system increases. When temperature decreases, the amount of thermal energy in the system decreases. So they track with each other. They're proportional to. If we want to change, and those of you who've seen the gas laws lecture, this will look familiar. If we want to change that proportional to sign to an equals sign, we can't say that they're equal at this point because, so why did I write that there? 1 joule is not equal to 1 degree Celsius. If we want to write this as a mathematical equality, we need to multiply one side of this equation by a constant number that will convert temperature units into energy units. So this constant C has energy units of joules per degree Celsius. All right. This constant has a name. All right. C is called the heat capacity. All right, this is the heat capacity. It is defined as the amount of energy right, in joules required to raise the temperature of a sample by 1 degree Celsius. All right, so heat capacity is measured for a specific object. All right, so this coffee mug will have a heat capacity that will be different from every other coffee mug, even other porcelain ones, because this coffee mug has a certain size and a certain mass, and a different size coffee mug will have a different capacity for heat it can absorb because it's a different size, different mass, all that stuff. All right. So heat capacity, you have to measure for each individual object, because even if they're made of the same thing, because they'll be slightly different sizes, they'll have slightly different heat capacities. Now, heat capacity is not the most useful thing. It has some uses, but typically it's not, because we don't want to have to measure the heat capacity of every sample of, for example, water we use. It'd be nice if we could have a more general unit, and we do have a more general conversion factor. We have something called the specific heat capacity. All right. The specific heat capacity is defined as the amount of energy, starts out very similar, the amount of energy in joules required to heat 1 gram of a sample by 1 degree Celsius. All right, this 1 gram inclusion is clutch, all right? Because now you don't have to measure the heat capacity for every body of water you're looking at. You can just know the specific heat capacity, which is the amount it takes to heat up 1 gram of water 1 degree Celsius, and that'll be the same no matter where your water's coming from. And when you know that, you can just multiply by the mass of your sample, right? By however much you happen to use. So the conversion factor between heat capacity and specific heat capacity is this. You'll notice that heat capacity has units of joules per degree Celsius. Specific heat capacity, I guess I forgot to put that on this page. Specific heat capacity has the symbol for specific heat capacity is CS, where S is whatever that thing is. So if you're doing specific heat of water, you do C subscript H2O, for example. So the conversion between, so specific heat capacity has units of joules. I do not want that to be blue. That's an ugly J. I can do better. Joules per gram degree C. All right, so specific heat capacity is equal times the mass of the sample, right? Times grams is equal to the heat capacity, because you'll notice that grams in the denominator here cancels grams up here in the numerator, and now both sides of our equation have their unit. So you can take this expression that relates heat capacity to specific heat capacity and substitute it into our equation for thermal energy transfer, which is thermal energy transfer is equal to heat capacity times your change in temperature. And once you make that substitution, you get this expression: Q, thermal energy transfer, is equal to M times specific heat capacity times delta T. This is commonly called Q equals MCAT, because the delta kind of looks like an A, and so it looks like the word cat. So you'll hear people say Q equals MCAT. I might even say it in lecture, and I'm just referring to this, which is the equation that we are going to be using to do problems with thermal energy transfer. All right, so let's start doing this. Let's start applying this equation to some examples. All right, so consider the following example. 10.0 grams of water is heated from 25.0 degrees Celsius to 28.3 degrees C. How much energy is transferred? Question mark. Is this process endo or exothermic? All right. So now there's a piece of information missing. There's a critical piece of information you need to solve this problem that isn't included as written. And I will always give these to you if you need them on the exam, unless, of course, you're trying to solve for it. But the book doesn't. So you'll have to look up these specific heat capacities for substances yourself. So that's why I left it out of the problem in the first place. So if you're doing the homework problems from the book that are just there for your practice, and you feel like you don't have enough information, look up the table of specific heat capacities, because that's probably what's going on. The specific heat capacity of water is 4.184 joules per gram degree C. All right. Now, anytime you're doing a new problem, the most important thing you can do is identify what you are trying to find. All right? And here, we're trying to find the thermal energy transferred, right? We're trying to find Q. Let's look at what we're given. We're given, when you look at the original problem, an initial temperature. Right, we have a T1. We have a final temperature, T2. We have a mass up in here, and you'll always either be given in the problem or you'll be able to look up for yourself the specific heat capacity. So, Angelina, that is an excellent question. Yes, they're totally. So Angelina just asked, is there a reason why the heat capacity for water is the same number of joules in a calorie? And the answer is yes. Turns out a calorie, that unit of energy, was defined by the specific heat capacity of water. So water has a specific heat capacity. And in the English system, they measured that amount of energy, how much energy it takes to raise 1 gram of water by 1 degree, and they made that the base unit of energy. So 1 calorie is required to raise water's temperature by 1 gram of water by 1 degree Celsius, and they said that's what we're basing our energy unit off of. And so that's why, since the specific heat capacity of water is 1.000 calories per gram degree C, then it follows that when you do the unit conversion, it's 4.184 joules per gram degree Celsius. So that is the reason why that is the case. So we've been given our mass, which is 10.0 grams. We have a initial temperature of 25.0 degrees Celsius, a final temperature of 28.3 degrees C, and we have a specific heat capacity. There's another very important piece of given information. There's an equation for calculating the amount of thermal energy transferred. Q is equal to mass times the specific heat capacity times change in temperature. And if you look at what we're given, we know mass, we know specific heat. We haven't explicitly been given delta T. However, we've talked about this in this lecture. Any change in is a final state minus our initial state, and we have both of these so we can calculate change in temperature. So we have all we need. And again, the algebraic expressions for specific heat, the algebraic expressions for thermal energy transfer and change in temperature have provided us a roadmap for solving this problem. You always want to write out your algebraic expressions when you're trying to solve a word problem. All right, so first, let's calculate our change in temperature. It's 28.3 degrees Celsius minus 25.0 degrees Celsius. And my calculator tells me that the answer is 3.3. The question is, does that have the right number of sig figs? And the answer is yes. When you're subtracting, you look at the last significant digit in each number. For both of these, it's in the first decimal place. And my answer has its last significant digit in the first decimal place, so there's no rounding needed, and no zeros should be added. It is correct as is. Delta T is 3.3 degrees Celsius. Now I can calculate my thermal energy transfer. 10 grams times 184 joules per gram degrees Celsius times my change in temperature, which is 3.3 degrees C. You'll notice that all of my units cancel. Degrees Celsius cancel with each other, and grams cancels with each other, leaving me with joules, which is good because I'm solving here for energy. So 10 times 4.184 times 3.3 is 138.072, but I can only keep 2 sig figs because of my change in temperature. Oops. There we go. So I can only keep 2 sig figs. So I count off my first 2. 8 is going to round up. So my answer is the amount of thermal energy transferred is 140 joules. All right. And if then I am being asked, is this endo or exothermic? You determine whether or not you're endo or exothermic by the sign. This is positive. My sign is positive, so this is an endothermic process. It has nothing to do with how big or how small the change is. It's only determined by the sign. Angelina, great question. She asked, does the change in temperature and Q, do the change in temperature and Q always have the same sign, or can heat capacity be negative? Heat capacity is never negative, so Q and change in temperature will always have the same sign. Excellent question. All right, so this was a very good kind of introductory problem, but I want to give you one that's next level, and we won't have time to work this problem today, but I want to write it out, you can give it a shot on your own, and then we'll return and do this together in lecture on Monday. So this is kind of a next level. These are called calorimetry problems. So consider this next level example. 15.0 grams of aluminum are heated and placed in 125.0 grams of water. If the temperature of water rises from 25.0 degrees Celsius to 33.0 degrees Celsius, what was what temperature was aluminum heated to? All right, and as always, I wrote this in the style of the homework problems where they don't give you the specific heat capacities, but on exams, I always will. You won't have to look these up. The specific heat capacity of water, we already know, is 4.184 joules per gram degrees Celsius. The specific heat capacity of aluminum is 0.903 joules per gram degree C. All right, so with that, you have enough information to solve this problem. Be forewarned, this one's a hard one. This one is a particular challenge, so if you can crack this on your own, props to you. You have reason to flex. But I really recommend trying this. Give this a shot before lecture on Monday. And because students usually get stuck at a very specific point in this problem. And if you've attempted it, when you see me work it, you'll be like, oh, and it'll make that much more sense, and it'll congeal it in your mind. It'll cement it in there. You'll learn it better. If you don't try it and you don't get stuck, you'll see me do every step. It'll seem easy and logical, but then when you try to do one of these on your own, it will be more of a challenge for you than if you had tried, gotten stuck, and then see how to work past that challenge. Okay? All right. That is all I have for lecture today. We'll close here. One last thing. One last thing to be aware of. So I'm just looking at where I am in my lecture notes, and this Monday. This Monday, we will cover work. So at your leisure this weekend, I would hit up the Chapter 5 lectures. It's not a big deal if you don't, but it will definitely make the gas stuff that we're talking about probably make better sense. So that would be my recommendation. All right. I will see some of you tonight in office hours. There's no lecture, nothing planned, just an open office hour to get all your questions answered, last minute questions before you start the exam. And if I don't see you tonight, I'll catch you on Monday. Later.